So welcome, everyone. I think we are going to go ahead and get started. So before I start talking, first of all, my name is Rita Blake. I am the Manager of Education here at the California Nanosystems Institute. Before we start, I actually wanted to throw it over to our Executive Director, Sonia Luna, who wanted to say hello and give some remarks to introduce the event today. So let's thank her for her time.
I don't think you should be applauding us. I think you should be applauding yourselves. For the adventure that you went on this week. I understand you've been doing a lot of hands-on work with nanoscience and then working with that knowledge to try and communicate better in terms of nanotechnology. So people in the room who know me well are going to chuckle because I'm going to tell you a story, okay? So being able to communicate in scientific terms is really, really important. It's important if you're a scientist because you have to be able to not only communicate with people at the National Science Foundation, the National Institutes of Health, and many other private and public organizations from which you, as future scientists, may be seeking funding. It's also important that you be able to translate that high-level scientific knowledge that you're going to learn throughout your careers, throughout your scientific endeavors. It's important that you be able to work and communicate with the layperson. And I'm going to raise my hand. I'm a layperson. So I've been at the California Nanosystems Institute almost 3 years now. I'm just going to tell you my undergraduate degree is in applied math, so I can subtract and add pretty well. I have a minor in violin performance, so I have fun on the side. And I have one of those things called an MBA, which is science and strategy. Nowhere in there did you hear an ology. It's no biology, no physics, any of that kind of stuff. Although I took classes in that, but I'm by no means an expert in that. So my message to you with regards to learning, with regards to communication, is as you progress in your scientific endeavors, don't be afraid to ask questions. Because if I hadn't asked questions when I first got here of the scientists, what is an MBE chamber? What does that do? What's a nanovault? What do you mean you might be able to cure pancreatic cancer? How are you going to do that with nanotechnology? Those are literally questions I asked, and I continue to ask those questions almost on a daily basis. And for me, being able to admit I need to know more is a really important part of my job, because then I have synthesis between the business and administration aspects of what I do and the science that we're trying to support. So I wish you the best the rest of the afternoon on your presentations, and we're just really happy that you all joined us here at CNSI. So have fun.
So for parents and friends and family who are here for the first time and may be entirely unfamiliar with where you are, welcome to the California Nanosystems Institute. So we are unlike a lot of other buildings and institutes on campus. So most of the time when you hear department in the context of a university, you think about an academic department, like physics, biology, chemistry, engineering, etc. We are not that kind of department. We don't grant degrees here. What we do instead is we are a research institute that fosters and facilitates collaboration amongst different faculty all over the spectrum of sciences and engineering. So we have faculty that come here from medicine, from physics, from life sciences, from biological sciences, from computer engineering, from all over, to come here and do research that is all centered around the topic of nanoscience, which is science at the nanoscale, which, as I'm sure all of your sons, daughters, friends, and family will be able to tell you at this point, is a very, 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 very small scale. And they will be able to tell you much more about that if you ask them. So I encourage you guys to talk to them about what they've learned. because they've learned quite a lot. It's been an extremely busy week. So before I tell you more about what we did, there's some people first that I have to thank. So first of all, our program director and instructor of record, Dr. Sarah Tolbert, who will be joining us shortly and will be certainly asking questions of the groups that she gets to hear present, and I will also be asking questions. And we also encourage friends and family and students to ask and answer to ask questions as well. Also, our program coordinator, Dr. Elaine Morita, who was extremely instrumental in working with me to get everything coordinated behind the scenes to make sure that everything runs smoothly. Because if you guys ever have the chance to run a program like this on your own, you will learn that it is a lot of work and a lot of moving pieces to put together. So I'm very thankful to have her help. And also the support of our directors, Dr. Jeff Miller, and our executive director, Sonia Luna, who you just heard from. There's also a lot of staff that were working with us behind the scenes to help things run, and I have to thank them as well. Jeremy, our events coordinator, Lucas in AV and IT, Nikki, our director of special projects, Kevin, our events manager, and Mark, who is our digital media producer and is also the person that is very helpfully helping us live stream this event. So to anyone watching us on the internet, hi! And also thank Mark if you're watching. So with that said, so the program itself is a lot of work packed into a very small period of time. So over the course of 5 days, students basically did one of two things at any point in the day. They were either doing an experiment in the morning each day on a different nanoscience topic, or in the afternoons, they were doing some type of activity to help connect the lab that they did to the greater context of how is this material that I made studied and characterized, or how is this material that I made relevant to anything in the real world, or how is this material that I made actually made in a real bigger industrial laboratory or out in industry. Because it's one thing to get to learn an experiment and do an experiment, which is extremely important and the foundation of science, but it's another thing, especially at the high school level, to be able to understand what that experiment is and means outside of the context of just a class. So with those two things put together, they then, at the end of the day, would take what they learned and had to do a very interesting homework assignment, which they're going to be showing you guys and using today for their final presentations. They had to do an analogy of the experiment that they did in the morning that is primarily visual with very little words and cannot directly or should not directly reference any actual terminology. And this seems like maybe kind of a silly exercise, but as Dr. Tolbert will tell you when she comes up, it is extremely relevant to actually getting people to understand your information. It's something that scientists actually have to do very often when they publish. And it's something that's really vital to keeping science alive as something that is understood by people and relevant to people. So with that, I want to bring Dr. Tolbert up to say a few words as well. So let's give her a nice thank you.
Hi, so sorry, I just want to say a few quick words of welcome to the parents who are here and say hello again to the students who are here. So my name is Sarah Tolbert and I'm a professor in the Department of Chemistry and Biochemistry and in Material Science and Engineering, and I'm the faculty director of our education program here. So for the parents who are here, how many of you have no science background? Okay, so you are our primary audience. So the goal of this is to communicate complex concepts to people who have not had all the background and all the training to understand all these concepts. And so for those of you who are presenting, your goal is not to impress people with all the super big words you learned during the week. Your goal is to convey to your audience new meaning. And if they understand you, no matter how simple it is, you have succeeded. And this is what we as scientists need to do more of. We're really good at talking to other scientists, perhaps less good at talking to everybody else. And so in the process of this week, our goal was to teach everybody in the camp both a bunch of really cool new science and to teach them something about how to convey it to everyone else. So I am going to be here for part of the talks, and I will try to ask hard questions. I can't stay for all of them, so if I am not here to ask hard questions, then everybody else has to take up that mantle. And the rule, so parents have to ask questions and, well, okay, students should ask questions. You guys know too much to ask the right questions because you actually know the experiment. The people who don't know the experiment, you have to ask questions. And the rule is there is no such thing as a stupid question. If something is unclear, it is absolutely not your fault. It is the fault of the presenter. And so you completely get to ask them about that. Anything that you don't understand is a fair question. Okay? And so to make this interesting though, you got to ask some questions. And you've got to give the students an opportunity to explain. Because sometimes when you say it the first time, it just doesn't come out quite like you wanted it to, and that's perfectly fine. You get multiple chances, but you as the audience have to help point people towards where we need those extra opportunities for explaining things. So to all our participants, I hope you've had a phenomenal week of doing nanoscience, and now we get to see what you're going to teach for us.
All right, so with that said, let's go right into it. So presenters, when you get up here, please speak into the mic because we are live streaming this, as we mentioned. So if you are not speaking into the mic, then people who are watching virtually cannot hear you. So please talk into the mic. If you turn, please turn, but keep talking into the mic. Don't do this because then people can't hear you. So keep talking into the mic. So with that said, team one, Kristen, Julia, Katie, please come on up. And let's give them a round of applause.
And I would just add that if you feel stifled leaning over a mic, they do come out pretty easily, and you can just hold it, and then you can turn it with you, and then just put it back in. So
yeah, and this one especially moves, so you can.
Yeah, but you can just take them out of the little containers, and if you're not as tall as Rita, which I am not, you can also tip them so that if you don't want to hold them. But it does matter. They're super short distance mics.
Okay, so we did a analogy on biotoxicity, which is basically the effects of toxic things on living organisms. And so in this drawing, you can see that there is an island, and there are enemy armies and Navy and Air Force attacking it. And the army, which has 700 people, is it's too big to fit inside the barrier, so it's not able to inflict any damage or very little damage on the island itself. And the Navy, which has about 100 people, which is much less, is able to inflict more damage, but not as much, not quite a lot. And the Air Force, which has 450 soldiers in it, is able to inflict the most damage and is able to basically destroy the island.
The army represents silver powder that we use to attack the cell. So the barrier of the cell is the membrane of it. And so the army is too big to enter the cell because, like the powder, it's too big to actually inflict any damage onto the cell. And then the Navy represents ions because it is able to come into the cell through protein receptors because it has a charge like other proteins that are accepted into the cell. And it inflicts damage onto the cell itself, but not as much as the nanoparticles, which is represented as a helicopter, the Air Force. And it inflicts the most damage because nanoparticles have a lot of surface area, so they can put a lot of ions into one nanoparticle, and they enter the cell through a process called endocytosis. And so they inflict the most damage on the cell. So as you can see, it destroyed the most. And at the top, the legend says gray and silver, and that represents the Army because gray and silver, it's that color because it accepts the longer wavelengths, which makes the particles bigger so it cannot enter the cell, versus the nanoparticles, which is light yellow, so it absorbs the shortest wavelength, violet, so it is small enough to actually enter the cell and inflict damage.
So we really liked this analogy that this person drew, and we really liked the drawing. We just had a few suggestions on how to make it even better than it already was. Firstly, we were just a little bit confused on the truck that's on the top right of the image, as you can see behind the Army, and we just felt that it was a little confusing because it didn't have a really big purpose. The second thing was that we thought that they could add some more damage shown in the Army panel on the bottom left, because although the Army, which represents the powder, is not able to physically enter the cell, it still is able to inflict some damage, which we felt that they could maybe add a little bit more. And finally, we thought that they could add a full view of the Navy panel, of the full view of the island, so that we could compare the damage between the Navy and the Air Force. Thank you.
Okay, so we are open for questions. Okay, I'm going to start with a question. Okay, so you guys did a great job. So first off, you talked about, I came in 2 minutes late. Did you talk about, we're saying goods and bads and.
Yeah, so I told them before they were going to present that they should talk about what was good about the thing and then what they could do to enhance it.
Yeah. So for everybody, if it's your picture, no analogy ever captures all of the physics of a system, because a cell is not an island and silver is attacking, but it's not an army. And so no analogy is ever, ever, ever perfect. That's intrinsic to the process. And pointing out where an analogy fails is not saying it's bad. It's just saying what are the limits of the analogy. So if it's your picture, don't feel bad. That's part of using a cartoon to describe science. It's always not quite right. So I would say my first question for you is, there's some great things about this analogy, and then there's some things that just are sort of fundamentally different than the real system. What is the biggest thing that's fundamentally different between this analogy and the real system? And the thing I'm thinking about involves scale.
Okay, so the tank itself and the Navy ship and the Air Force, in real life, they're relatively close to the same size, but silver ions are actually way smaller than nanoparticles, and nanoparticles are smaller than the powder. So they don't show as the different sizes of the forms of silver.
Yeah. So the real system varies by orders of magnitude. So you want to show like attack, and so you're using this analogy, but like an ant attack versus a military attack might be more similar to the real size differences between silver nanoparticles and powders and ions. Like, ants, rats, and actual ships are more close to the real sizes. So that's a limit to this kind of analogy. Okay, now other people have to answer. So, by the way, parents, you don't get to go to the reception unless you ask at least one question. So, who has a question?
I don't understand what the number of soldiers has to do with anything.
So basically, in the actual experiment, we have a cell, and there's these different ways that silver is trying to enter the cell to create oxygen radicals that basically destroy the cell membrane. So this, in the analogy, there's the different amount of soldiers is representing the different sizes of the silver that's entering. So for the Army, it's 700 soldiers, which is the largest amount of people like in the analogy, and the Army represents powder going in, trying to enter the cell, but it physically can't, so that's why it's like can't enter the walls. And the navy, which represents the silver ions, is the smallest, which is why it has 100 soldiers. And the nanoparticles, which is the Air Force, has 450 soldiers, which is the second largest and the most effective because it can't enter the cell and still has more, and is still bigger and has more ions than the silver ions, which are smaller.
But the real system is probably 1 10 to the 10th and 10 to the 24, as opposed to differing by a factor of 7. So that was the question I was asking. The real differences in size are way bigger, and that's a limit to this analogy. But that was a perfect question. One more question?
Any channels on that on the island that the soldiers can go through it, or they just go from on the cell? Are there any specific channels they go in and out?
You guys talked about that. Is that somehow captured in this picture? You can talk about both the real system and whether any of it is captured in the picture.
So actually, in the actual experiment, the silver ions go through active transport in order to get into the cell. So I think we are assuming that the Navy can. It's like going through certain channels, but it just doesn't do enough damage as the Air Force does.
Okay. Any one other question?
Do you have any concept of the time that will invade or whatever?
Is there anything about time scale? Either, is there anything you want to say about time scale, or is there anything about time scale in the picture?
Sorry.
In general, this is a pretty fast process. So when we did the experiment, it usually took about maybe 5 or 6 minutes to see like real results from this. And how we did it was we had a manometer, and it had the carbon dioxide from the yeast that was being expelled from the yeast, and it was moving water that was in the tube, and you could measure, and that happened fairly quickly.
So is that captured at all in the picture?
Not really.
Not really.
Okay, but then I can ask a different question. This is always a question, so be warned if you're thinking. Is there a way you could imagine adding that to the picture that would capture some differences in time scale?
Yeah, like you can put like after 10 minutes, like above the Navy or below like where it says Navy, you can put like after 15 minutes of attacking, so you can actually say how long they attacked to show how the time scale. So you can just add that.
Yeah, or you could have things that move. You could intrinsically make the delivery vehicles, some be slow or some be fast. So you could build it into the things that are attacking, make to reflect that time scale. That's probably the more intuitive way to build it into the cartoon itself. Okay, we should move on. Thank you guys for doing an awesome first presentation, and good job, audience.
And can we also acknowledge the artist who did this lovely drawing, if they would like to stand up? Stand up. Mehak, good job. Is there any concept that you intended to put that they did not discuss? They pretty much got it? All right, nice. Cool. Well, good job. All right, so our next team is Sorcha, Karen, and Hen. So let's give them a round of applause.
Hi, everyone. So, the drawing that we have was based off of the first experiment we did, which was measurements in nanoscale and also indirect measurements of the nanoscale. So starting off in the image, we have a really sick person, and they're really sad because they're sick, and they have to go to the pharmacy and pick up their medicine. So the medicine says on it, if you're 6 feet tall, you take 6 pills, and if you're 5 feet tall, you take 5 pills. And the next two images capture the person figuring out how tall they are based off of indirect measurement, which Karen will talk about more. So based off of this, they decide to take 5 pills, and the pills get into their stomach and attack the virus that's making them all sick, and the virus dies, and all the pills and the medicines inside the pills are really happy about this, and then the person's happy again. So, yeah.
Okay, so basically the building and the person is showing indirect measurement. The height of the building and the height of the length of the shadow is being used as a ratio, and then the height of the person can be found because there's only one variable in the next one, like you already have the length of the shadow. So that's indirect measurement, and then the second and third row is basically showing how things that happen on the nanoscale affect things that happen on the human scale, like, yeah, so it changes the appearance of the person. And it also could show, since in the experiment we did, we put oil on water covered in baby powder to show how amphiphilic molecules arrange themselves in a very thin layer. And so the pills kind of self-assembling in a line against the bacteria could be amphiphilic, if you think about it that deeply. Yeah.
Alrighty, so we did really like this analogy. We thought it was fun and cute, but there are a few things that we thought could have been added to the drawing. So firstly, the thing that Karen just addressed, amphiphilic molecules, are basically molecules where one side is hydrophilic, which means they like water, and one side is hydrophobic, which means they don't like water. So if you put them on water, you end up with a layer that's one molecule thick. And we thought this could have been demonstrated through the pills, but it might have been more clear had they actually added a layer of water underneath the pills to show how, for example, the black sides were underneath and touching the water and the white sides were above the water. And second thing we think could have possibly been included is this day we also got to look at a very cool microscope called an atomic force microscope, which basically, instead of using light or electrons reflected through lenses or electromagnetic fields to show really small things, uses what is basically a very tiny finger that actually goes down to the point of a single atom and shows the structure of things on the atomic scale, the nanoscale, by literally moving the finger over the structures. And that was really cool, and we feel like it perhaps could have been included here by maybe showing an examination of the bacteria where perhaps we get a little glimpse into the inside of the bacteria and we see what they look like on the inside through contact with the pills. So we liked the analogy.
All right. Thank you, guys.
Okay, so for everybody, and I tell all of my graduate students this, when you're done, say, "Thank you for listening," because your audience is terrified, paralyzed. Are they done? Are they not done? Will they tell me if they're done? So just say something that says, "Okay, we're done now." You're allowed to clap.
Thank you for listening.
Yeah.
Yay!
That's a thing. But you're not the only one who doesn't do this. Like, everybody has to be told for just say, and like professors who've been professors for 30 years still stand up there and then just stop. And then the whole audience just like, wait, finally somebody claps. Okay, so be smarter than those guys. Okay, so we are open for questions. You don't make me start all the questions.
All right, let's go.
So one of the other concepts that was really big in the lab was the idea of constructive versus destructive interference. Did you guys think of any possible way that within this universe of analogy that could be incorporated?
You know, we actually did brainstorm that a little bit, and the thing we considered was perhaps having the bacteria and the pills represented as two different wavelengths, which is how interference works. So if the wavelengths match, it increases the amplitude of the wave, basically makes it stronger, and if it's opposite, then it decreases the amplitude of the wave, so it cancels it out. And we could have the bacteria basically on one wavelength and the pills on another. So when you have the pills and the bacteria together, that's destructive and it cancels out. If you have too many pills, then that amplifies the effects of the pills and you end up with a stomach ache from taking too much medicine. If you have too many bacteria, then you get sick, as so adorably shown in this analogy.
I have one clarification. Constructive and destructive kind of happens also, like when it's on like the same wavelength, but like when the troughs and the peaks kind of meet. So yeah, that was just one clarification. That's it.
I think you'd have to be a really good artist to describe what you just described, because that's a hard concept. I'm not. I don't think I would ask for this question, because I don't know how I would add that to a figure that already has a whole lot of concepts in it. But just for everybody, the simpler the concept is, the more likely people are actually able to get it out of a cartoon. So it's almost impossible to make really complicated concepts in a drawing. I'm not sure. I don't think I have an answer to Rita's question.
I'm not sure if I do either, but I was just curious if they thought of anything.
That's a lot of our time of brainstorming with like no results.
Yeah.
So, yeah.
That's okay.
So I understand the indirect measurement approach shown in the drawing. Now, in the description of the experiment, you talked about a special microscope that used like a probe that went down to 1 atom width. How did you actually do the indirect measurement in the course of the experiment? What equipment did you use?
So we didn't actually use the microscope in the experiment. That's a really big, expensive piece of equipment that we just got to look at because we're kids and they don't want us messing with it. So in the experiment, what we did is basically we had a tub of water and we put a really thin layer of baby powder on the surface, and then we put a drop of oil on top of the water. And because oil and water don't mix, it formed a very thin, 1 molecule thick layer on top of the water. So if we could measure the diameter of the circle formed by the oil, and we knew how much volume was in it, then we could calculate the thickness of the layer based off the volume and the diameter of the circle, which gave us the thickness of 1 molecule, because the layer was only a molecule thick, and then we just assumed it was a perfect circle because we don't want to do complicated math, and then we could calculate the size of 1 oil molecule. So.
What was the baby oil?
So the oil was just like vegetable oil, and then the baby powder was so we could see the difference between the oil, where the oil was and where there wasn't any, so we could measure the circle.
That was a good description. So when you are presenting these things, do remember that your audience has not done the experiments, and so just like that, give them some fill-in of what the experiment actually is when you're giving them the analogy. That helps a lot. Okay, any more questions? One more question? Okay, I'm going to ask a question. So the ratios and heights of shadows and things is actually a pretty good analogy with this kind of geometric indirect measurement. What's the fundamental problem with it? What do you usually not know? You're trying to get the height of a person. But what do you need as inputs for this particular measurement?
Well, you need measurements of like,
So you need to measure the surroundings of the person to figure out the height of the person, but when you're working on the nanoscale, you can't take measurements of the surroundings of things. So you have to be able to work from the outside in to calculate size, and this is really just working from like left to right.
You need to know a lot about the surroundings, particularly you need to know the height of a building, which is not necessarily so easy to do. But the concept of that kind of indirect measurement is actually a very good analogy. Okay, any other questions? All right, let's thank these guys for a really nice presentation. Can the author stand up?
Oh, yes, thank you.
And what would you, is there anything you'd like to add?
Excellent. All right. So team 3, Lauren, Chen Yu, and Peyton. We also now have a laser pointer for you. So you can push it here to turn on. Please be careful with it and don't point it at people.
Hi, I'm Chen Yu.
I'm Peyton.
I'm Lauren. And our drawing is called the Polymer Park. And it's an analogy for our lab called about biopolymers, where we make a gel using polysaccharides and different concentration of calcium ion.
So in the picture, we have both kids and adults and both girls and boys that are at a park. And some of the kids are on a play structure that you can see in the top left corner.
So some of the people are holding hands forming a circle, and some of the people are holding hands forming a line, and some people are standing under the sun and are hot, unhappy, and are not holding hands, and then some of the people are standing under a tree and are cooler and are happy and are holding hands.
And in the middle of the playground, you can see kids trying to leave to play on the structure on the top left. And on the bottom left, there's less people than on the playground.
So this picture is a metaphor for the experiment that we did about biopolymers. So the kids that are shown actually represent the calcium ions that we use to form the gel, while the adults are iota-carrageenan, which are the other part that we use to form the gel. The park is the place of interaction, and when the adults and the kids are holding hands, that represents them forming bonds to form the gel, and it forms the bonds of different lengths to represent the different strengths.
So the sun represents the heat that prevents the solidification of the biopolymers, and the shade represents the cooling effect, which allows the solidification, which is represented by the holding of hands.
So on the left side of the wall, there are less people, so less people are able to make the bonds. And on the right side, on the main playground, there are more kids, which means more calcium ions, and they are able to form more bonds. And they are stronger, and they form quicker.
So the bonds that are represented actually go in a repeating pattern of adult kid, etc., for however long they are. And this is actually true for the experiment we did, where polymers have to be in a very exact repeating pattern for them to pretty much work. So when the kids go to the playground to play, they have to leave their groups, and that eventually breaks the bond, which represents how if you put in an enzyme, it can actually degrade the gel from our experiment, and it won't be a gel anymore. It'll go back to being in the liquid state.
So what we liked about this illustration was portraying the family as representing the polymer, and portraying the adults as iota-carrageen, and the kids as the ions that linked the adults together.
And what I like about this picture is that kids trying to play on the structure, and it makes sense in our real life that kids wants to play.
One more thing that we liked is how there's the creativity of showing the temperature change, how it can affect the polymers using the sun and the shade.
A possible improvement that you could make is breaking it into panels to clarify certain important concepts.
And another improvement could be make the arrow point to the exact place or from the exact person.
So to conclude, our group really appreciates the creativity of the artists to create this metaphor to represent the lab that we did on biopolymers. Thank you.
Okay, questions? You guys are going to make me start this one again, right? Yes.
So the playground, that represents the enzyme? Is that right?
The playground just represents, it does represent the enzyme of the kids wanting to go there to release the bonds and break the polymer apart.
But it says source of ions.
So we took the source of ions to represent of like, that's why they're all there. That's the place of interaction. And that's what brings the kids and adults to that one part of like the park.
Yeah, I think maybe it's actually just that. It's the source. So in your experiment, so say you just imagine that playgrounds are sort of an infinite source of children, and parents aren't actually connected to particular children. They just need any child, and they can just go steal one from a playground. How would that be an analogy to the actual experiment in the way you did it?
It's like the concentration of the calcium ion, which are the kids, actually attracts the polysaccharides, which is represented by the adults. So actually, the kids attract the adults to make the bonds.
So what do you start with in your experiment?
Polysaccharides.
And then what do you add?
Kids.
Exactly. So I think maybe it's just like kids have to come from someplace. Where do kids come from? Playgrounds. Okay, other questions?
In your experiment, what does the wall represent in the actual experiment itself?
That's actually what we are trying to figure out, and we thought about it and realized like on the left side of the wall there are less people, and on the right side is the main playground, which has more people. And that maybe we said in our conclusion, basically we want the creator of this drawing to make more panels so that you can see a separation between important parts. It's not just a wall on the main playground, so that you might thought that's a part of the.
Yeah, but in fact, we should focus not on artistic choices, but on science analogies, because one can break into panels, or one can just make regions of a picture that represent different parts, and they're both. We should try to not focus on the sort of artistic choices, only on the limits of the analogy, like, you know, how is child not a calcium ion, as opposed to sort of how you graphically. But so given that we now understand that the wall is separating a region, it's like a panel, and that's a perfectly great way to do it. What is the region on one side of the wall in terms of the science? How is that different from the region on the other side? What were the two things in your real experiment that represented the main park versus the other side of the wall?
So on the left side, you can see less kids, so they form less bond. And in actual experiment, we have 5 different flasks, and they all have different concentration of calcium ions added into it. So on the left side is the less concentrated flask, and the right side is the more concentrated ones.
Yeah. So, okay, other questions? No,
Is there any meaning in the fact that the children and the adults were used? Is it to just represent size, or is it just the analogy of bonding?
Yeah, it represents actually polysaccharides are really small sugar monomers linked together, and that usually polysaccharides are many sugars linked together so that their size is really big. But calcium ion is only one atom, so that's a difference in size.
So my last question is, any significance to the whole holding hands thing? I think there's one more connection you could make that has to do with the nature of the calcium ions.
So it could be the charge, because calcium ions have a very specific charge. They can only go towards the part of the polysaccharide that has the opposite charge. So when they attract to that specific point.
And what is their charge?
So it's positive for calcium ion and negative for polysaccharides.
And do you remember what positive charge it is?
Positive 2.
And maybe you could go one step further with the analogy, because it's +2.
They have 2 hands.
Yeah. Okay, so this was awesome. This picture, I just want to say, captures so much physics in one picture. Could the author stand up? That's a really... So, good job, excellent job explaining, and also excellent job doing a group discussion of the topic and going back and forth. So, good job to everybody.
All right, so next team is Team 4, Cameron, Williams, Schuyler. There's your pointers here if you want it.
Okay. Hello. What's your name? My name is Schuyler.
I'm William.
I'm Cameron.
And I'm trying to get this microphone off. There we go. Okay, so this drawing here was for the experiment that we did yesterday, which was on photolithography. And very briefly, photolithography is the process of using light to pattern materials and etch them out so you can create very, very small structures on the nanoscale for industrial purposes.
All right. So this artist drew a, I think that is a wooden block, and I'm shaky. Wow. And that is a paintbrush painting like a coating. And in the next arrow over, we see fire, and it is only burning the part that is not that does not have a coating. And in the next arrow, the same thing is happening, and we can see that it's making a staircase, and we see that the staircase is very large in scale because the height of one step is about the height of one person. So that is way too big for a staircase. And so, but here we have, they are making the paintbrush thinner by cutting it with a knife. And so if you make the paintbrush thinner, then the coating layer is also thinner, making the fire able to make a staircase that is able for the humans to actually walk on, that is like not so tall as the original. And here, and there is a comparison of a dirty environment and a clean environment. And so in the dirty environment, it says that this person is getting stuck, but in the clean environment, they can walk up. That is, yeah. Okay.
Awesome. So just a Photolithography itself, it's about a 6-step process, and basically what you start off is a 3-layer wafer. It has a substrate on the bottom, which basically is just sort of like a base. It just holds it together. And then the next layer in our experiment was a layer of copper, and then the layer of that after that was a layer of photoresist. So photoresist is a chemical that changes its properties when interacted with light. So our photoresist, if you shine light on it, it would actually dissolve and turn into a liquid, and then you could remove that liquid later. So the first step of photolithography is to coat it in photoresist. So for us, that was already done. And then the second step is to put on a mask, which is sort of like a pattern. And the mask is just certain black lines and dots, and then certain negative space. And so light can shine through the parts that aren't covered by the mask, and it shines through to the photoresist, which basically dissolves the photoresist, leaving under it a pattern that was like sort of made by the mask. And so after that, the next step is to develop the photoresist. So you dip the whole thing into a chemical, and it washes away all of the photoresist that was dissolved by the light. And then after that, you etch the whole thing. And so the whole point of putting the photoresist on was to have certain parts be protected from the etching. And so the etching material goes into the copper that's left behind by some of the dissolved photoresist. And you etch the parts that you want to etch out of the copper. And then so that's the etching step, and then the step after that is just to finally strip away the top photoresist, and what you're left with is the whole etching of copper that you wanted from the beginning. And this is used mostly when you're trying to make computer chips, so like for Intel or something like that, they have to make very, very tiny wires, processors, resistors, and photolithography is how they're able to do that. So with this metaphor here, it sort of goes into 4 steps here, so that's one of the limitations we'll get into in a moment. But putting the paint on is equivalent to putting on the mask. It basically prevents putting on the mask and the photoresist. It's what prevents the rest of it from being etched. So as you can see, the fire is like etching all the way down through the copper, through the material. So putting on this little paint protector thing kind of protects that specific spot from the dissolving. And then it sort of works its way down all of the stairs. So the fire burns down a little bit on one step and then next, and that's how it gets its structure there. And then, so the fire is like the etching. The fire is what burns through the wood, and the etching is what sort of burns through the copper and gets dissolved away. And so the other concept here is that you can have different sizes of nanostructures. So here we have the large structure that's sort of too big and not very functional because you can't climb steps that are 6 feet tall. And then here we have the nanostructure that's much smaller, and it was made by smaller tools. So what's important is being able to use smaller tools to be able to get the exact size of structure you want, which is usually very small. And in real life, ways you can do this are using electrons potentially instead of actual light, because light is limited by its wavelength, which is still really small, but because we're on the nanoscale, it's not quite small enough, and it's still really big. So it's important to be able to get very fine resolution there. And then the last concept, there's a lot of concepts here. The last concept is the clean room. So if you've ever seen one of those factories where they're making processors, the clean room, the scientists are wearing bunny suits, and it's very sterile. There aren't any particles. And that's because if you have dust on the nano chip, then it sort of messes up all the circuits and it makes it unusable. So here, the dust and muck makes the stairs unusable, and the clean is much better.
All right. So this is the good, the bad, and the interesting of this metaphor. All right. So to start off, what we liked was that the paintbrush metaphor, it was very easy to tell that the scale size, when the scale size is changed, it's easy to switch from 10 feet to 2 feet, and it's much easier, and that directly relates to the stuff we used in class with photolithography, except it's not on the same scale. It's not from 10 to 2. It's much larger scale of difference. And another thing we liked was that this person was a very talented artist, and that it's very easy to tell what's going on. Unlike us three, we're not very good at that stuff. So, and also the clean room is very easy to tell, as the person's stepping on gum as he's going up, and the next stair is very clean. And so some things that we thought could be improved, although photolithography is a very complex process, which is very hard to capture in one analogy. So this had 4 steps actually, but the actual process has 6 steps, which is one of them is spinning, which is not included in it, and developing. But that's okay because, I mean, I think us 3 easily got what the process was, but, and like I said before, it's very hard to get all of those steps into one easy analogy. And one other thing that we didn't understand was the paintbrush, what it's actually painting. We weren't too sure if it's wood or it's like fire retardant, which is how they got the steps. But other than that, we thought the drawing was very unique and artistically pleasing. But with a few improvements with labeling and some more steps, then it would be very clear and concise. Thank you.
Okay, I would just again say, try to talk about it as the limits of the analogy. So you guys just talked about it, but I ask you again to say slightly different. So this analogy captured some of the essence of the photolithography process, but it left out some, not the mechanics like spinning, but it left out some of the essence of the photolithography process because that's just, this analogy cannot capture them. So what are the things that this analogy did not choose to capture?
So this analogy, it didn't capture the development phase. In actual photolithography, when the photoresist is exposed to light, it turns to liquid, but it's still it's still part of the structure, so you have to find a way to wash it away. And in our experiment, we put it in developing fluid, but that's not seen here. In fact, I think if the paint is the photoresist, then it's never washed away altogether, and instead we get the etching, but we never get the development phase.
Okay, so that would be one, the removal of the pattern making component. So there's another big concept in photolithography that is not tried to be in part of this.
Is it the mask?
What's the name?
The mask of...
No, what's the name of the process? What?
The entire
experiment is called?
Photolithography. So the photo.
The photo. So how could you possibly incorporate that if you wanted to? Let somebody else.
We could have a blueprint of what the structure is supposed to be like, just like we have with the photoresist. Before doing it, you have what it's supposed to be, and you transfer the material.
Yeah. Some kind of pattern transfer is sort of the idea. This has all the lithography, but this analogy is not trying to have the photo pattern transfer, and that's okay. You cannot capture all of it, but so those are the kind of things to say. What are the limits of this analogy? What are they not trying to capture, but is part of the real experiment? Okay, questions from the audience?
So one of the other big concepts that the lab talks about is when you guys made a thick wire versus a thin wire. So can you talk about that part of the experiment and what you learned from it? And then is there a way that that can be put into this analogy?
Okay, so so in the actual experiment, the thin wires had more resistance because sort of like how a smaller pipe has more resistance to water flow, it's harder to put as much water through. The thin wire has a harder time putting through a lot of current. So the thin wires have more resistance, whereas the thick wires have less resistant and can do more current. And to be honest, I know there are a bunch of extra concepts that the artist could have chosen to do, and I kind of feel like putting the different sizes of the wire in some kind of metaphor would be a little outside of the scope of the metaphor of stairs.
So what if the stair steps were like really, really small? Like what if the increments were like barely visible? Then what would it be instead of a staircase?
Like a ramp.
So what if the ramp were really steep?
Then it would be sort of like the stairs that are really steep, and it would be mostly unclimbable and unusable.
And then it'd have more resistance to people going up. Yeah.
It had more resistance. Or they could have been like skinny stairs and a whole pile of people in a line trying to get up. You've all been like stuck at an escalator that's too skinny and nobody can get up. So those are just ways to think about where you could put in extra concepts. Okay, questions from the audience. We need a parent question. Yay.
Did you use different wavelengths, and how about the time, the exposure time?
Okay, so exposure time is, it's not really something you want to change, because if you overexpose, then you sort of just go too far, and then it just sort of ruins it. And if you underexpose, then you can't quite get the pattern you want. So exposure is just like a very specific time that I think they just figured out through trial and error, to be honest. And then different wavelengths of light is portrayed here with the different sizes of paintbrush. So a smaller wavelength of light or a smaller paintbrush can get finer resolution on the stairs. It can get the smaller steps that have better function.
Okay, any more questions? All right, good job for this team. And can the artist stand up? Is there anything that you would like to add? Okay, good job.
All right, so next team before our break is Team 5. So Kristen, Rhea, and Rachel. So let's give them a round of applause as well.
Okay, so hi, I'm Kristen.
I'm Rachel.
I'm Rhea.
And so ours was from the experiment from today, earlier today. So it was about supercapacitors, and so we all know the problem with like solar and wind energy is that it's really hard to store, and so we use most of electricity like during the night, but the sun is obviously out during the day when it's when we're not using as much electricity. So the solution for that would be to try and find a very efficient way to store all that energy. And so there's several different ways that they have up here. They have batteries, which have low power but have very high energy. And then there's capacitors that have high power but low energy. And then supercapacitors, which is what we were working with today, have medium to high power but medium energy. And so a way to change a capacitor to a supercapacitor is to increase the area and decrease the distance between the plates. So it was kind of just like a quick overview of like the main part of our experiment. And so what we see here is they have Battery City, which has heavy traffic, and it's a 20-mile-per-hour road because we have the city plan on the side, which is very like twisted and turns, and there's a lot of turns, so they can't go as fast. And then there's a lot of cars. And then the next one over in Capacitor City, there's moderate traffic, so it's kind of like in between. And then it's a 60-mile-per-hour road. And then it's slightly more efficient with like not as many turns in the road, and it's more like straighter blocks. And then the bottom one, which is Supercapacitor City, has no delays, and it's also a 60-mile-per-hour road. And then it's a very efficient city plan because there's a lot of different streets which the cars can go to and not have all be on one path.
So this drawing is comparing batteries, capacitors, and supercapacitors to cars driving on the road. So in the first box, there is heavy traffic caused by the winding roads, as you can see in the city plan. So in the top left box, you can see the cars driving on the road, and there is a lot of traffic. This is because batteries are really slow and chemical reactions take a while to happen. The cars represent charged particles, while the sides of the road are plates. The bus you can see driving on the road is big compared to the cars next to it, representing a bigger area. In the top right box, there is moderate delays because capacitors have high power but lack energy. And in the bottom box, supercapacitors are like the perfect middle between capacitors and batteries. They have medium to high power and about medium energy. There are no delays due to increased area represented by the city plan.
So for this drawing, there are several things that we liked and there are some limitations. We liked how they made the city plans and how they drew the roads. It really showed which cities were more efficient than others. Also, they showed like the areas for different vehicles. Like in Battery City, the bus was bigger. However, for the analogy, they used scientific words for the cities. But in Battery City, they really show how the cars are going slower, and in Supercap City, the cars are faster. However, it doesn't really show how that supercapacitor is more efficient than the capacitor. It's also confusing how there's more traffic in supercapacitor compared to the capacitor city. But overall, we really like the how they were able to make such a simple drawing out of this concept.
So, thank you.
Okay, questions?
A battery should have more energy than a supercapacitor, right? So why are there more cars in the supercapacitor?
I think that was kind of one of the things we weren't sure on, because like there's only like one car in capacitor city, and then like there's a lot of cars in supercapacitor city. So I think we were trying to figure out like
but wait, are they all cars?
I mean, I guess there's like, I think Rachel was talking about how like the different sizes of the cars were representing like a bigger area.
But do we think they're all cars? The bottom, they look like cars, and the right, they look like cars. What about the left?
I guess they could be like bigger, like trucks or something. That
Or buses.
Yeah.
Buses. Okay, so then if you made the left buses and the bottom, the right to the other two cars, could you use that to make the analogy map better onto the science? So I think what's you're talking about power, which is speed, and energy, which is capacity. So specifically, say what you're going to map it onto, speed or capacity, and how you might be able to use that.
Well, I guess batteries have a lower power, so like I guess the buses could be taking a lot longer on the road or something. Yeah.
Okay, but now map it onto, so that's good, but then also map it onto capacity.
Well, also buses can hold more people. So by showing the buses, it shows that it could carry more people, or in this case, particles.
So what are people analogies for?
The electrons.
Yeah. So the people can be electrons, and so then you can have the higher capacity of batteries because you're filling these big buses. Other questions? Yes.
Okay, so the first one in Battery City, it's 20 miles per hour, and then the other two are both 60 miles per hour. And that's because both the capacitor and supercapacitor have kind of both medium and high power, so it's kind of supposed to represent that they're going like similar speeds, but they just have different like energy.
So that's good. I would modify the speed limits. So because the supercapacitors and the capacitors are not actually the same.
Yeah.
So how would you maybe modify the speed limits?
I guess make the capacitor a little bit higher because it's kind of that peak point of the power, and then the supercapacitors can be just a little bit lower and they go all the way down to like similar to batteries.
It actually can be a lot higher. The capacitors can go super fast.
Okay.
The capacitors are very, very fast systems. They just don't store very much. The supercapacitors are that compromise of storing a little more and being not too slow. But capacitors are actually way faster than supercapacitors. You just don't have the electronics to measure them, so you don't know that. Okay, one more question. One more question, then we can have a quick break. Who's it gonna be? I don't know if the parents have earned their coffee break yet. Okay, students, can you ask a question of your lab mates? Oh, you guys are gonna make me do it. Okay, so in terms of the analogy, there is a direct in terms of the city plan, which is trying to say sort of what are the pathways. It's a really cool idea. I might modify the city plans a little bit. So how would you modify the city plans to better reflect the real pathways in the system? Or which one would you want to modify?
Well, maybe for the supercapacitor city, because in the city plan, you can see it's really condensed and tightly packed. I mean, it is organized and it's not windy, but I would feel like the capacitor city would be better.
So the supercapacitor has lots of, it's organized, but it's got lots of little things. What were you saying about the capacitor part?
Oh, I was just saying how it should be more spaced out like the capacitor city plan.
Actually, I think the supercapacitor city plan is actually pretty right. It's got lots of places to put electrons or cars. And a supercapacitor is a nanoscale thing with lots and lots of places to put electrons or cars.
Oh, I guess the capacitor doesn't really have as much space to hold the electrons, so it should probably be not as many like roads around.
The capacitor would probably just be one road because it's just a flat surface. It doesn't really have any other place to put electrons. And the battery, it's a little different, but the windy road is a pretty good analogy because there's just only so many ways for current to get through a battery. And so I'd probably modify the city plan to make it, for the capacitor, to make it even more different from the supercapacitor. Okay, all right, so good job explaining this. Can the author or artist stand up? All right, artist team, that's right. Okay, so team, what things would you like to add to their description?
Yeah, so at the beginning, when they didn't point out like the buses, which you noticed, yeah, there are more people with a battery, as explained when they were talking earlier about more energy, but it's slower in power, while the supercapacitor is both high in energy and power, and the capacitor is high in power but not energy. And so we were going to point that out, but now that you guys pointed it out, I think we're pretty good.
Okay, good job. Thank you all. Okay, so I should also just point out, the reason that this was drawn by a team is because they did this experiment today, and then they drew the picture today, and then they prepared the presentation today. So these guys get, both the drawers and the presenters get an extra round of applause. Okay, so we're going to take a super short break, like 5 minutes total, just to stretch, run to the bathroom, and then we're going to resume.
All right, so let's go ahead and get started again. So if Team 6 could come on up, Ayana, Jingjing, and Sangeeta. And let's give them a round of applause as well.
I'm Ayana.
I'm Jingjing.
I'm Sangeeta. Okay. For the first part, it's a picture of, it's a toy factory, and there's 3 workers separated by 3 walls, and they represent the cells. And so they're monitoring the amount of toys that go into the bucket. And so the rival on the far right is kind of like a silver in general. And so he poisons them first with the poison to the touch, like powder, I guess. And then it affects no one, so no one's hurt and it has no damage on them. And then in the next scene, he poisons them using gas, and it affects one of them. And so one of them dies. But the toys are still being processed, so it didn't affect them too badly. And in the last scene, he is making food poisoning, and they all end up eating the food. They all die, and it's the most effective way to kill the rival. And I should mention that in all 3 of the scenes, they're representing different scenarios in different points of time. As you can see by like the clocks in scenes 3, 5, and 8, I think. They all have clocks, and they're all showing the same time.
So basically, like the whole metaphor is that like the little cell or the workers are each individual healthy cells, so the experiment we did on biotoxicity is that we had 3 different samples of yeast cells, and we exposed them to like silver powder and silver nanoparticle and silver ions. So for the first part in this drawing, this is the little poisonous things to touch are like the silver powder. So the silver powder is too big, so the cells like recognize that it's too big and it's like dangerous, so they reject the powder from going in, so none of the workers got killed. And the second part, this whole row is representing like the whole silver ions. So like the poisonous gas, because ions are way smaller than the silver powder, so it's representative of like poisonous gas. So it's effective, but not effective enough to kill all of them, so only one of them dies, but like the production level goes down. So the way we measure how healthy the cells are during our experiment is by using like a pressure sensor. So the numbers are basically the same thing as what we did in our experiments. And the last one is what happens when we expose it to nanoparticles. So it was like extremely effective in that like it killed all of them. And when we did our experiment, like there was no change in carbon dioxide levels. So that means like all the yeast cells were basically dead. And yeah. Also the different ways that the ions go through into the cell is by going through like the protein pores. So like the cells think that like the ions are food, so that's how they take them in. And then the nanoparticles are small enough so that they go through endocytosis, so that's how the nanoparticles enters the cell.
Okay. So in this analogy, we saw a lot of things that we liked, but we also saw some limitations. So things that we liked were we liked how we saw the different levels of exposure of poison
towards like the workers. It kind of showed the different levels of silver powder and the effect that they, the silver and the effect that they have on cells. We also liked how how they measured the toy production to kind of measure, to show like how, which was analogous to like the health of the cell. So yeah, and a limitation that we saw was that like the different levels of poison, they don't exactly show like the actual scale of how the difference between like the ions and like the powder and the nanoparticles. So yeah, thank you.
Okay, so audience, you have now seen these experiments once before. And so now you are more educated about, so I should point out, so they only did with 5 days, they did 5 experiments, and there's 11 groups. And so you're gonna see all of them twice and one of them 3 times. And so as we go through them multiple times, you're more educated and you can ask even more questions. So the fact that you've seen it before does not get you out of asking questions. It makes you have less excuses for not. So the floor is open for questions.
Nicely presented and illustrated, but you said the production of a factory was representing the health of the cell. And if that's the case, I wondered how in your experiment did you measure health of a cell? Was it just whether the cell was alive or dead, or are there different degrees of health?
Okay, so the way yeast work is that they take sugar and then they like feast on it basically, and then they produce waste or like carbon dioxide. So we connected to like a tube with water in it. So the more it produces carbon dioxide, the more it pushes the water upward, and we measure like how much it pushes the water up as like if they're alive or not. So yeah. Does that answer your question?
Okay, so then go one step further. That was awesome. What is the specific analogy between what these guys are making and what the yeast made, and how are those products the same or different?
So basically, the amount of production of toys represented the amount of production of carbon dioxide. So in the silver powder, it's not able to get into the cell, so the yeast is still able to produce carbon dioxide, just like they're still able to produce toys. And the ions has some effect on it, but not as big as the nanoparticles, which is why it's still able to produce some toys or carbon dioxide in the cell. And then with the nanoparticles, it's not able to produce any toys.
Okay, but so then what is the one, what would be a limitation to that analogy in terms of how is production of toys and production of carbon dioxide different?
I guess like maybe like when they're exposed to the nanoparticles, they don't
no, just as a product.
Maybe because carbon dioxide is waste, and
That's
toys are like...
Yeah, so one is actually a product they're trying to make. Carbon dioxide is actually a waste product. And so in that, so the issue here is whenever you make an analogy like this, and these are all beautiful analogies, they can't capture everything. So in one case, it's a waste product, and in the other case, it's a purposeful product. And the point of pointing those out is if you're teaching somebody who knows no science and nothing about the system, then people take analogies very literally, and they'll say, oh, well, so then the cell stops producing something useful like toys. Well, actually, in the experiment, this cell just stopped like breathing. So it stopped producing a waste product. And so it's worth pointing out where the analogy just isn't exactly like the experiment, because they will always be places where it is not exactly like the experiment. Okay, that was a great question. Next question. So there's some new parents here, and I thought I would just mention to all the new parents that the rule is you don't get to go to the reception unless you ask a question. Just one. So I'm trying to motivate the parents to ask some questions here. Okay. Okay, so I will ask one question while you think. Okay, so what is, so there's a lot of beautifully captured concepts here. What is a concept that is not as much captured here?
Probably like the way that the silver powder had no effect at all in the picture, but eventually like it has a little effect in the experiment because it damages the cell in a little bit of a way. So in the picture, it could have maybe shown one of the workers having like a broken arm or still being okay.
But it actually didn't do too much. There's a sort of a fundamental concept of the experiment about the differences between the things that work and didn't work that is not particularly trying to be captured here. So what is that concept? Given that this is a summer program in
Could you repeat the question?
Nanoscience.
Could you repeat the question?
There's a concept that is not trying to be captured here, that is not particularly well captured in this cartoon. That's sort of fundamental to this experiment. What's different about the different things that do and don't work?
Maybe like how in each case they're damaging the cell in different ways. When in the experiment we damaged it in the same way but more and more.
Or like, would it be like the concept of like the color and kind of?
Well, I mean, those are all good concepts. Since this is a lab on nanoscience, what concept might not
So, okay, so the scale of the powder, nanoparticles, and ions.
Just the concept of size.
Yeah, size.
Is not what's in here, and this the thing that differentiated. And like I said, you don't capture everything. This captures a lot of beautiful things, but that's something to point out, is that the whole idea of size is not really the distinguishing feature. Whereas in the last analogy, size was the thing that it was trying to capture. Okay? So the different cartoons will capture different aspects, but just point out the ones they don't capture. Okay, one more quick question. Students, you guys get to go to the reception anyway because you worked real hard all week. All right, we will thank these guys. Who is the author of this? And is there anything you would like to add? Because there's a lot of detail here. Okay, good job, everybody.
All right, so next team, Team 7, Sarah, Eric, Mackenzie. Let's give them a round of applause. And I'll remind you there's a laser pointer if you would like it, so if you're trying to point things out.
Do you want to go that way?
Okay, so our picture is based on three main concepts. So the first one is indirect measurement, which is basically using a given quantity to estimate other quantities on either a larger or a smaller scale. And then another aspect is how features at the nanoscale can affect features at a human scale. And then the last kind of concept that this picture addressed was the idea of constructive and destructive interference. So in the picture, you can see in the top left corner that there is a key where one fish equals 4 circles of fish food. And then you can see in each bath or pool, there are varying levels of fish food and fish. So in the upper bath, there are more fish, so it makes sense that there would be more fish food. And then in the bottom bath, there are less fish, so there are less fish food. And each bath is 1 million liters. And then on the left side, you can see that there are 2 kind of groups of fish, and then one group has both lines of fish swimming in like a similar wave pattern, which is successful, and then there is another group of fish where their wave patterns are kind of contrasting, and then they end up bumping into each other, which obviously isn't successful. And then in the bottom left corner, you can see a person holding a bottle of oil, and they're pouring this oil into a pool. And then there are arrows bouncing off the oil, which is representative of how light waves would bounce off the oil in this case.
Okay, so as Mackenzie mentioned, the first topic of this picture is indirect measurement. So in the simplest terms, indirect measurement is using things we know to figure out things we don't know. So in this picture, we see one fish correlates with 4 food, and in the 2 tubs, the artist established that the tubs are the same size, so we don't care about the volume of the water. But we see that in the first tub, there are a bunch of dots, way more dots than the second tub. So using indirect measurement and knowing how much food each fish eats, then we know in the first tub, there's way more fish than the second tub. And our second topic was, how does things at the nanoscale affect the way we perceive things on a human scale? So that would be this small drawing down here. So in our lab, we measured the layer we measured the height of a monolayer. So we used olive oil, which mainly consists of oleic acid. Oleic acid is an amphiphilic molecule, so it has a hydrophobic tail and a hydrophilic head. So imagine my hand is the surface of the water, then the hydrophilic head, the water-loving part, is in the water while the tail is sticking up, which is the hydrophobic part. So when we say monolayer, that means just a single film of these molecules are lined up on a solid surface. So in our experiment, we did 2 trials, one with olive oil diluted in ethanol, and the second one, olive oil just by itself. In this picture, the person pouring the oil is just pure oil. It wasn't diluted with ethanol. That's why when the person poured it, it formed this cover that seems shaded in, but really it forms a rainbow surface. It's iridescent. Since a drop of oil, technically, if it has a very large area of water, it can form a single monolayer, but since the tub we used was too small, the layers started overlapping. That's why it affected the way light passed through the layer, creating this rainbow effect. Otherwise, the main point of the lab was diluting it in ethanol to make the volume of the oil so small that even in our small tub of water, when we put 1 drop of olive oil in, it can still form this single layer, and it should be transparent. And the last topic was constructive and destructive interference, as shown by the path of the fish. And the second part of the lab we did was using a laser beam and optical grating. So we shine the laser beam through the grating, and the grating separated the laser beam into different waves. And so if you hold a piece of paper to the end of it, then you would see like a row of dots, like a bright spot, a dark spot, a bright spot, and a dark spot. So when the light is separated into waves, then there's constructive interference, which means waves, the height, the peak of the wave corresponds with another wave's peak. Therefore, it becomes a greater amplitude, which is demonstrated by the light, the parts where the laser light shows. And destructive interference is when the peak of the wave and the trough of the wave, they cancel each other out, which creates these black spots.
And we really liked this drawing, and we thought it illustrated the concepts very well. And one thing in particular is that you could very clearly see how the troughs and peaks line up for the constructive interference. But one thing that we thought maybe could change is that with light waves, for example, the different waves combine to increase the amplitude. So in this case, they could have maybe drawn a greater wave or something resulting from that. A limitation of this analogy is that fish themselves can't combine, but that's okay. We thought the destructive interference was very well illustrated as well, with the fish canceling each other out. And we also liked how the person standing at the pool is able to see the interactions at the nanoscale level on how we could see it with our visual eye or visibly ourselves. But another limitation of this drawing is that because it's from like our point of view, we're not able to see the hydrophobic and hydrophilic interactions themselves. We can only see how it's forming a layer on top.
Yeah, any questions?
Oh, thank you.
Thank you.
Okay, we are open for questions. Rita gets to ask the first question.
Okay, sure. So one of the things I was thinking about with this drawing is I wonder if there's a way to use the fish to actually show amphiphilic molecules and the monolayer if you use the fish in the food. Can you guys think of a way of doing that where you could get some type of alignment with using the same things that were already in the first part of the analogy?
Oh, well, I guess the fish would want to go to the food, so I guess they would all line up, like with their heads on the top and maybe tails on the bottom. So they, like if the food floats on the surface, then they'll all line up to get access to the food.
And so in that case, like the head or the mouth of the fish would be like hydrophilic because it's attracted to the fish food, which is like representative of the water, and then the bottom half of the fish would be hydrophobic.
So then it would literally kind of be a hydrophilic, head and tail sort of analogy.
Literally head and tail kind of analogy. So the in phase and out of phase here, it's very clear, but I think, okay, so phase and waves are not an easy concept because they're not a concrete thing. So, sorry, I have, it's a little picture and I can only half see it. So in terms of the Auna phase, is there a way you guys could think of to modify the Auna phase to make a physical picture of destructive interference?
Wait, could you?
So in destructive interference, what happens to the wave?
Well, it cancels out, so like if the wave is going like this, then they'll both just kind of like flatten out and they...
So how could you maybe capture that in the fish?
Well, since we all know, like when fish die, they kind of just float in a straight line. So when the fish, they collide, they give each other concussions, they die, and then they kind of just float in a straight line.
They could also just disappear. They could actually cancel each other out.
Yeah.
So I should point out for the audience that this experiment was actually had two parts that were totally separate experiments that were both about measurement at the nanoscale. And so for people who tried to capture both aspects of them, they are actually fundamentally disconnected because they were two experiments. In the future, we should probably encourage people not to capture both halves of them because they are actually totally separate experiments. Okay, so other questions from the audience? Yes.
Yes.
So when you described that, you were talking about how it broke up into different wavelengths, but since the laser is, two within experimental parameters, one wavelength, how does the diffraction gradient work for one wavelength?
I guess I wasn't very clear. So the diffraction gradient, it's the grading. It's kind of like an obstacle or slit.
It's like
And multiple people, yeah. Other people should answer these questions too.
Yeah, so it's like a bunch of like little slits, and so diffraction is like defined as when like a light wave passes through either an obstacle or a slit, and it like causes the light to like bend sort of, and so the thing that we use, it was basically like it was a bunch of, it was like a crisscross pattern, so it was a bunch of different slits. So it caused it caused the laser to kind of diffract in several different directions.
But these gratings were like very, very small. And with this, we used the indirect measurement to determine that the spaces were like on the nanoscale small.
So I guess to put this in a much more understandable context, so you know how like over a bridge there's often those arcs and water flows. So when water enters those, so water at first is like this continuous waves, but when it enters the two slits, then they kind of break up to their own individual and it slowly gets larger. So that's why when you go to the other side of the bridge, you see like these points of intersection and they slowly cancel each other out until it goes back to being one big wave.
Oh, and I don't think we mentioned this, but after we shined the laser through, the constructive interference made like 3 dots, or like dots appear in a line. So the laser was like split very orderly because of the nanostructure.
And then what could you measure once you saw the dots?
We measured the distance between the 2 dots, and using the height that we held the grating on, then we could use trigonometry to find the distance between the gratings.
Okay, so another form of indirect measurement of finding a nanoscale dimension. Okay, any other questions? If not, can our artists stand up? Is there anything you would like to add? Okay, good job, guys.
Thank you.
Thank you.
All right, team 8. Andre, Archit, Munib. And let's give them a round of applause.
Okay, so we did the lab on biopolymers. So the first image you're looking at the very top is an empty fish or empty food for the cat, and there's no fish in there, and the cat are spread out, and there's only 4. And as you progress down, there's a couple fish in the cat bowl, and so it shows the cats like coming together, like forming pairs, sharing the fish, and they. If I can see. They whisper, meow, and then the third image. There's a lot more fish in the food bowl, and as you can see, there's a lot more cats forming, ties together. Like there's a lot more on the top, and there's also different cats on the bottom. There's black coat, stripes, polka dots, and they're screaming meow, versus the top. And the last one, you can see thunderstorms breaking up the cats, and so they go in different directions and lose like the pattern that they were in.
All right, so the biopolymer experiment was where we used calcium ions of different concentrations to bind together the iota carrageenan, and so those monomers were held together by the calcium ions. And what we found was that the larger the concentration of the calcium ions, the stronger the gel was. And in addition, we also used a protease to break down a glycerin gel, and that broke it down into a liquid. So in this comic, these cats have no food, and the food represents the calcium ions, and that's why the cats are not together. Then in the next panel, they get some food, so these weak interactions are formed between these cats, which represent the monomers. But as you go to the third panel, you realize that more food creates a longer chain and likely stronger, as depicted by the little lines that show the strength. Then another major concept that we learned about was that different types of monomers can come together and form a polymer as well. It doesn't have to be exactly the same. So these cats represent when it's exactly the same, and these cats represent the different types of monomers. Also, the size, the loudness of the meow represents how strong the bond is. So the cats have more energy, and as a result are louder. Then another concept was that that heat and cooling can separate certain polymers. So here, the cold from the thunderstorm will separate these cats. Yeah.
This artist kind of included really a lot of good concepts in their art. So first of all, the cats and the fish was really good to represent the iota carrageen and the calcium bonding together, because I mean cats like food, so kind of that the more food they have, the more closer they're going to be. They did a good job of showing that. And also with the meows, like a smaller meow is a weaker meow, so it's kind of showing like a weaker bond between that. I mean, it works. And a bigger meow, it's a stronger, connection. They're kind of united. And in the last one, I think it's kind of the other way around. So like one of the things they didn't really clarify, and like they didn't really show in this one, was that the heating actually separates the biopolymers, and the cooling actually keeps them together. So yeah, that was just one thing that they didn't show, but it was kind of hard to depict in this one. Also, maybe scaffolding, like they could show it, maybe the cats in a circle instead of a straight line, or like making a pyramid. I don't know if that would work. Yeah, but overall it was pretty well done, in my opinion. What?
The types of food.
Oh, I don't know, that's like art or something. I don't want to like diss them on that.
Yeah.
Oh yeah, thank you.
Okay, questions? All right, I will start with the question. Oh, there's one? Where's the question? Okay, go for it.
So I was thinking, since also in the experiment we used the protease to break down the enzymes, that potentially be what the thunderstorm represents rather than...
Yeah.
Yeah, so it's a bit unclear as to which one the artist wanted to represent, because it could suggest the degradation from the protease. But we're assuming that because this molecule is the iota carrageenan, which did not break down from the protease, they meant to show the cooling instead.
So it is legitimate to sort of mix concepts in a cartoon, because it's a simplified version. What is distinctive about cats as animals in terms of their likes and dislikes? I don't know if any of you guys have cats.
No.
No cats? No cats in your group. Okay, anybody who has a cat, what do cats really hate? Water. They really don't like water.
Oh.
So, given that, it's still a little, you have to sort of grasp at it. How might that change the interpretation of the bottom panel?
So like it probably like in that context means that the water is driving them apart. So like as in so like in the real experiment, the protease was the thing that drove the bonds apart.
Yeah, I'm guessing that it is more representing the protease than thermal, just because of the specific negative interaction between cats and water. Okay, so my question is, you talked about it, which is mechanical properties, as something that was sort of the key thing that changed when you changed the amount of linkers. So any idea how you could add that to this cartoon, other than by the size of a meow, in terms of actually representing the mechanical strength of a network?
Maybe like the more food you eat, the bigger you are, or like the stronger you are. I don't know. That work.
That could work. Other ideas? Brainstorming. There's no right answer here.
There could also be a different structure from the number of calcium bonds, or yeah, like that.
Although actually it is the same structure, it's just more connections.
Mm-hmm.
There could be something trying to push them or trying to take something away, something that sort of indicates mechanical strength. Okay, other questions from the audience? We need one parent question. I'm a parent. I've been stuck in this situation too. I wouldn't do anything to you I wouldn't do to myself. Okay, Rita's going to ask one question. You guys get one chance to think. Oh, you have your own.
Sound good. Okay, so I don't know if you mentioned this when you guys were talking. I might have missed it, but I noticed that in the third panel, there's 2 rows of cats. Yeah. And one row of cat is all the same colors, and the other row of cats are not the same color. So what is that pointing out?
Yeah, one thing we forgot to mention was that for the additional concepts, it says biopolymers can be, when we were assigned homework, we had to include additional concepts. So one thing that we didn't say that was that the biopolymers form exact repeats or repeats of a certain type of monomer. So that's why we thought this person was trying to show that also with the different, like one's dark, one's striped, one's polka dot. So that's what we thought this artist was trying to hint at.
So there's a specific type of name for those types of polymers where you have like a certain patterned repeat. Did you guys learn about the name of that type of structure?
Yeah, it's the polypeptides.
In a sort of more general context, though, do you know what that is called?
The polymers?
So it is a polymer, but when you have the patterns of sort of different ones, it's a copolymer, if I recall correctly. So you're getting like an A, B, C, A, B, C, A, B, C. So when it repeats in that kind of regular order, that's a specific type of polymer where it's not the same monomer, but it's different monomers that can form a repeating pattern.
Other questions? Parents, this is your chance. Everything you want to know about biopolymers. Okay, what is the most common biopolymer that everybody in this room has interacted with? Or sorry, the most common biopolymer gel that everyone in this room has interacted with?
Gelatin.
Trade name?
Jello.
Jello. This was a lab on basically Jello. Okay, I don't know if parents are going to really get to go to the reception, but we got a few more talks to work on it. Okay, can the artist stand up? Hey. Are there concepts that you would like to add? Or anything you want to clarify about the rain and the multicolors?
Yeah, so for the rain, just to clarify, I was using that to like represent the protease because it's like cats, like you said, like they specifically don't like rain. So like I tried to make that connection.
Okay, good job, everyone.
Thank you for your meowsing drawing. I'm sorry. Trying to get people to get more excited about these. All right. So next team up, Team 9, Adam, Andrew, Kazuki. Let's give them a round of applause. There's a pointer circle if you want it.
Hello, everybody. I see you haven't had enough biopolymer, so we bring you more. I'm Andrew.
I'm Kazuki.
I'm Adam. So basically, ours is on biopolymers. As you can see, wait, where did the laser come? So as you can see, in this first one, there's a cake. And the second part of it, there's somebody, he's dumping strawberries onto it, make a happy birthday, spell it out of strawberries. And this is like how it comes out. There's 50 strawberries, which is like represented by that. Then a healthy person, which is represented by the word healthy up there, comes along. And they want to make it more healthy. So they first start off by taking out the strawberries, and it ends up with like 10 at first. And then when it gets to 0, there's just a dried cherry layer on top. And then they're like, oh, I just want to put cherries on now. So what they do, they put on the cherries instead, so that instead of having the strawberries, so they put it on there. And then at this point, what they do, they take this tool, and they're able to take off the icing layer. So then this is the final cake with the cherries on top, and then there's the cake layer. Then the child comes along, and you can see that because it says child right here. And they try to put raspberries on, but they only make one, and a lot of them just miss. And then after the cake is done now, so it's put into an oven, and it's put for 30 minutes at 300 degrees Fahrenheit, so that the salmonella will be broken up and destroyed.
Okay, so in our experiment, what we did is, so we took iota carrageenan and mixed it with calcium ions. So calcium ions have a positive charge, and iodocarrageen has sulfate groups which have a negative charge. So that is why those two attract and form a gel. So the forming of a gel is represented here. So what happens when the strawberries are put into the icing is that the strawberries and the icing kind of like form a bond. And when this person tries to take out the strawberries, he gets some icing that is connected to the strawberry. So that represents how the bond is formed between the strawberries and the icing. Okay, so another factor that we learned about biopolymers is that when we put in calcium, the iodocarrageen could form bonds much faster and easily. So normally, without the strawberries, the cake would take time to, the icing on the top of the cake would take time to bond together. But once the strawberries were added, it was easier for the icing to form a concrete shape. So that created this happy birthday shape that came off after the strawberries were taken off. Another thing we learned about biopolymers is that enzymes can break down specific gels. So the enzyme in this case is this tool that the person is using to take off the icing layer. So the tool represents the enzyme because it is breaking down the icing layer, and it is leaving the dried cherries and the cake layer. And this also represents how enzymes can only target specific things because the tool only took off the icing layer and not the dried cherries. So you can tell that the tool was only fit to take off the icing. Another thing that affects biopolymers is that certain biopolymers work better with certain ions. And in this case, when the child tried to put on raspberries, the raspberries couldn't form a good connection with the icing, which is why they fell off. But in the case of strawberries and cherries, they were able to connect easily with the icing. And the last concept that is represented in this drawing is how heating a biopolymer affects its structure. So when the cake was put into the oven right here, the salmonella evaporated. So that represents how heating a biopolymer can break it down, and that is what released the salmonella in this drawing.
Okay, sorry about the slight confusion with releasing salmonella. We meant to break it down. But further on, we have extensively analyzed this comic. By a little bit confusing, we appreciate the artist's ability to connect common cooking with the scientific topic of biopolymers. And furthermore, we see much more potential in this. Starting with the first slide, we see that they have the layers over here. We believe it may be easier if we were to perhaps add some details to these layers, such as a sort of wavy pattern to the top icing layer, or perhaps shading the cherries over here so to distinct them better. And they do show the heating process in the first panel. However, they do not show a cooling process. So we believe they could add on maybe 2 more to show it cooling and sort of settling in its final shape. And in the second and third one, we did mention how calcium, in this case strawberries, helps bonds form faster and stronger. Since there's no other comparison, we were thinking maybe use another fruit or maybe less of the fruit to represent that this over here is faster than if you were to use something else. Furthermore, in the fourth slide over here where he's taking off the strawberries, it could be made a little bit more clear if they were to add past outlines of where the strawberries were. And next you can see that we have happy B-Day, happy birthday, and back to happy B-Day. We were thinking maybe keep a little more consistency because it can get confusing at times, you know. And I'm not one to say with my art abilities, but maybe label this as a tool just in case, you know? And almost there. We have a couple point of view things over here. I don't know if you want to put that there, a little bit confusing at times. And that about settles it. Thank you.
Okay, so two things. I think that this is a perfect example of the fact that a scientist can explain anything. So, I'm going to have you guys explain this again, but I'm going to have you explain it as a different experiment. So, try viewing this as photolithography and seeing what you can do. Because I'm pretty sure this was drawn as photolithography.
Okay, so we didn't notice that this right here is supposed to be a template, I guess, to put into strawberries. So that represents the mask in photolithography, where you put the mask on the object you're changing. So that's the mask, and you put the strawberries in, which represents the UV light, which goes through the mask to create the pattern. And after that, let's see. So right here, we're under taking off the strawberries. It represents the process of etching, where they take the strawberries off so that the pattern is inscribed at the bottom, which is represented here. And then at the end, they also etch the icing layer on top, which represents the photoresist that is taken off at the end when the pattern is finished, kind of. Yeah.
Yeah, and then what do you end up with?
You end up with the Happy Birthday pattern, which used cherries, which was represented by cherries at the end.
So you end up with a pattern that was created, but then I guess is transferred to something else. And then the very end, what is the salmonella, the last panel, what it might be capturing? That is important for doing photolithography.
Well, the final step to get rid of salmonella appears to be like getting rid of bacteria, because bacteria, dust, even fingerprints can all cause huge errors when doing this sort of process.
Yeah, so it's the idea of using a clean room or making a clean environment as to make less errors in the process. Okay, so that was a good job of on-the-fly reinterpretation, but I think is a little easier to explain this way. Okay, do we have any questions?
I like to say you guys did like a very good job, but I just want to know a little more about how you think maybe the panel division and like how the steps on the image like coincides with the 6 steps or the steps of photolithography that we completed in our paper.
I know you guys are doing it on the fly, so don't worry if what you say is perfect. Just, go for sort of a discussion. We understand. It doesn't need to be a perfect, just start your thoughts. Good.
To us. Let's talk out loud.
So we don't quite remember the process that happens before etching.
So that's okay. Any pieces of it.
We believe is the process that is happening here.
Okay, well then just explain the other ones.
Okay.
Don't focus on the one piece you don't know. Focus on all the pieces you do know.
So this is the masking. They're putting the strawberries on. Or, okay, first here they're creating the icing in the oven, which is like when you spin the photoresistant on the substrate you're trying to create. So that is represented by the icing here in the oven. And then this is the masking phase. And then this is I think this is masking and exposure, and this is development. Not sure.
You can skip some and just go on.
I feel like this is etching because you're taking the photoresistant off, which is basically the icing layer that was originally on the cake.
Well, actually, I think the label there, sorry, says icing layer. What's on top of the icing layer? What are you actually taking off? Or, sorry, I guess you're taking off part of the icing layer. And then the last one? It's not necessarily a piece of the standard process. What are they actually doing in the end?
Oh, so the last step would be the cleaning because they're putting the cake into the oven so that they're able to clean out all the bacteria and salmonella.
But they're also utilizing the pattern. So I think they're using the icing pattern to attach other things. Okay, so can our artist stand up? Okay. And can you add to their description?
Yeah, so I thought both of your interpretations were great. It was originally supposed to be the steps of photolithography. So for the number 10, the last panel, that was supposed to be like for the equation for resistance, when you increase the length of that cake is longer than the first cake, you increase the resistance. And so I thought the best way to make a cake more resistive would be to add some analogies. You're cooking at the same time at the same temperature, and that's the one that ends up with salmonella because it's longer. That makes sense.
Any comments on the middle parts in terms of what, because they didn't get a long time to think of it in terms of photolithography. So are there things you can add to the explanation?
Yeah, so I think the seventh one, the second from the bottom, was he's taking off the icing, which is the etching, I think. And then the one to the right of that was just the final product of just having the substrate and then a little bit of the metal on top, in
All right, so we've got 2 more presentations to get through. So we'll move right along. Team 10, Damagi, Coco, and Josh. Let's give them a round of applause.
Hello. So the experiment that we did today that we're going to be trying to explain with this picture up here was we experimented with supercapacitors, which, in simply put, we took some carbon and attached it up to a bit of energy and tried to make it work and store energy and output. So I'll let you all see this while the picture is explained.
Okay, so as you can see in the first panel, it's a marathon, and you can see that there's a little kid at the end, and then somebody who is very familiar with running marathons in the middle, and then a lady at the very front. And the guy in the middle represents the supercapacitor, and the kid represents the battery, and the lady at the front represents a capacitor. And then in the second panel, you can see that the lady is starting to fall behind, and the guy has now taken over the lead. And then at the end, you can see that the little kid has short strides and ended last. The lady had average strides and ended in the middle. And the guy had long strides and ended first.
Cool. I'm going to take this off. It's going to be a little loud. So I'll give you a little bit of a brief background with power and how this relates to batteries and how this all relates to the picture up here. So power, simply put, is energy expended, and energy is how much stuff or how much potential is stored. So when you're putting this in terms of batteries or in capacitors, a battery basically stores energy, so does a capacitor, and then releases it somewhere else. This is what you do with your phone, with your car. You charge something up and then have the energy expended sometime later. So with a battery, as the group earlier was explaining, it has high energy but low power, which means that it can store a lot of stuff, but it can't really release it quickly, which a capacitor can do. Now, a capacitor has low energy but high power. And kind of in the middle of this, when you increase area and decrease the distance between plates, which we did a lot this morning with nanotechnology and getting stuff small, you get a supercapacitor, which has high-ish energy and high-ish power. Now, this kind of relates to all this picture you're seeing up here by the first runner going off to the very fast head start, the girl up there. We thought this represented the capacitor, where she got off to a very fast start. Now, as we keep going along, she kind of starts to fall behind. That's because she has she has high power but low energy, which means that her stamina isn't the best. Now we can see the person who actually wins the race in the very last one, that's going to be our supercapacitor, which means that he got off to a slower start, but because he had a lot of energy and a lot of power, he could stay moving for a very long time. Now at the very end there, who's lagging behind the entire time, that's her battery, unfortunately. And so yeah, so we also kind of analyzed the quotes and the strides at the bottom, which you can probably see better than I can. So with the quotes, the supercapacitor has run 20 marathons before, and that's kind of representing how durable supercapacitors are. They can go for, I think the statistic was 50,000 times, while a battery can only run like 5,000 times. So it's much, much more durable. Also, with the capacitor saying that she cannot keep up, that's because she has that lower energy and she simply doesn't have the power to, or the energy to keep up. And then at the very last part, or the supercapacitor is saying that he's pacing himself, and that's because he has a lot of power and a lot of energy. So yeah, and thus, I'll give you a little bit of a pun, the supercapacitor wins the race in the long run.
So overall, we thought the analogy was very creative and straightforward, and we thought the different speeds are very obviously representing the supercapacitor, the battery, and the capacitor, and the strides also really let you know that. And the distance of the race basically was also a very good way to explain the distance that electrons need to travel. But some limits on the analogy that we saw was we couldn't really see that it captured the relationship between the area of capacitors and the distance electrons need to travel, because as area increases and distance decreases, efficiency increases, and that's not really shown here. And we also didn't really see how power versus energy was demonstrated. because batteries basically have energy and supercapacitors have power. And we figured that people could basically be like running different races. So the battery could be running a longer race but running slower, and the capacitors could be running shorter races faster. Yeah, that's really all we thought. Cool. Thank you for listening.
Thank you.
Okay, questions?
What do the times represent, the actual times that it took them to run?
So I think the times were their attempt at demonstrating the power versus energy, and also just how supercapacitors are more efficient than capacitors and batteries. But I think that it was kind of missing that, like, batteries, while they are slower, they can also keep going for a longer time.
So, okay, so the times I think are like 5 hours, 3 hours, and 2 hours, which are like sort of real marathon times. So now if you wanted to make them like real battery and supercapacitor times, what would you change them to?
Oh, do you want me to answer?
Whoever.
Sure. So supercapacitors probably cannot run for 2 hours. That's a very long time. This is a marathon given, and this is trying to represent that they're better in the long run again. But realistically, they would have to recharge over and over and over again, but they can recharge very quickly in order to get there. So
just like order of magnitude, what kind of times? These are sort of long, medium, and short marathon times. If they wanted to be long, medium, and short energy storage times, like what times would you use for each person, vaguely, or just like order of magnitude?
Sure. In order of energy storage, the battery would definitely last the longest, as they have high energy and low power. Supercapacitors would go next. They have high-ish of both power and energy, and then the capacitors would go last, having very little energy but high power. That's why they run so fast but can't get very far.
But can you, one of you, the others of you guys, can you actually guess at times, not order of times, but actual times?
I mean, today in the experiment that we did, we lit up LED lights with our supercapacitors, and I mean, those only went, they would only be running for about a couple seconds, and then they'd have to recharge for like 30 seconds, and then again, they'd just be, the lights would run.
So supercapacitors order a few seconds. Everybody has a battery. What's the sort of time scale for batteries?
A few hours.
Hours. Okay, so we've got hours, seconds for the regular capacitor. Any idea?
I mean,
probably seconds or milliseconds.
Probably microseconds.
Microseconds.
So that was a great question, because like the Army one, there's only a finite scale that the real systems can have, but the science systems can be orders of magnitude different in scale. Okay, other questions? Actually, there's a parent. Parents get first priority.
So in both cases, I think the cartoon has done a good job of conceptually demonstrating the difference between batteries, capacitors, and supercapacitors. But could you explain a little more what the actual lab was like this morning, where you were exploring? You mentioned it a little bit. Could you explain what you did this morning?
So basically, we used a bread box. Yeah. Something called a bread box, and we basically put like wires, and we wired our own capacitors, and then after that we wired our own supercapacitors, and we basically just made an LED light, work by charging the capacitor and then running it, and we ran like parallel circuits after that with we had two capacitors together, and we ran parallel circuits to see that the light would run longer because there was more power.
So you actually made your supercapacitors. How did you make them?
I cannot remember the exact chemicals that we used.
Doesn't matter the exact.
Citric acid.
Just
Okay.
just a big idea.
Basically, we had carbon, which in our form, I don't know if we actually had graphene, but we had some kind of carbon base that could store energy, and then we had.
What was special about the carbon?
Play-Doh.
It was Play-Doh we like.
Well, you made it Play-Doh we like, but what was its what made it useful? Was it a big chunk of carbon?
It's a conductor.
Was it just a big solid piece of carbon?
It was powder. Yeah. or like powder that we made into like small bits.
The audience
Small
seems to know the
bits.
answer.
I told at the very first day. I told you what was the answer. The answer to every question.
High
gonna be
surface area.
It was very high surface area carbon. Told you it was going to be the answer to every question.
True. So with our high surface area carbon, we were able to store a lot of energy. I believe this calculations came down to our little chunk, like 2 grams of carbon, could store 500 meters squared of just surface area, which, if you think about it, like something in that big of an area can store something half the size of a football field. Was it?
2 football fields.
So
Oh,
that's
sorry,
the-
2 football fields.
That's how much surface area it had.
Yeah.
Then what did you store?
Oh, we stored electrons
You
on
stored
it.
electrons, and where did they sit? Why are electrons and numbers of football fields relevant to each other? Where did you put the electrons?
I'm kind of confused about that question.
It was on the carbon. I mean, yeah.
On the surface.
And so-
Surface
yeah.
of the carbon.
And so since there's high surface area on the carbon, we could fit a lot of electrons onto it and therefore conduct finish the circuit.
Good job. Okay, I have one more question. So there's a lot of dissing of batteries here, but in fact, batteries are everywhere and ubiquitous, and we're not throwing them all away for supercapacitors. So that means batteries actually do better in a whole lot of cases. So what race would the battery win?
Probably a marathon, actually.
Well, okay, but so this was, okay, I don't know what race this is. So given that this was drawn as a marathon and the battery didn't win, what race would the battery win?
Any long distance race, because they can last a lot longer, and they store more energy. I don't know if that's what you're looking for, but
Some
yeah, longer.
much longer race.
Yeah.
They totally, we use batteries for everything because they store way more. They're just slower. So a longer race, both of those guys would have been like just lying down on the edge of the road, and the battery would still be running. Yep.
When you first talked about supercapacitors, you said that they were better than capacitors for 2 reasons. First, you increased the surface area, and then the second thing you mentioned was that you decreased the distance. How did you use your chunk of carbon to decrease distance as well, or did you not take that into consideration?
So they're not necessarily better than capacitors. They both have their merits.
No, this is a different question.
Oh yeah. I know.
So
yes,
okay.
yeah.
Okay.
Just answering the first part. Yeah. So basically, we use the carbon to actually.
Sure, I can take it. So in normal capacitors, it's usually steel plates. And steel plates are kind of chunky. They are very big, very hard to work with if you're trying to make a small scale thing. The nice thing about carbon is that when it forms up with whatever chemicals we used, they could make very structures that had very small spaces in between what you call plates, or parts that you can have electrons jump between, I guess, and are being stored on. And so in order for this supercapacitor to be made super, we had a bunch of those little plates in a very small area.
So that was basically right, but I want to just get the true essence. So in a parallel plate capacitor, you have 2 plates, and the distance is just the distance between them.
Yes.
What's the relevant distance here? It's the distance between what? The surface of your carbon and what? What's sort of the other plate? And it's not actually a plate.
It's the electrons, right?
The electrons are on the surface, so that has one charge. What's the thing that has the other charge?
The electrolyte solution?
Yeah, it's actually ions in solution, and that's what makes the distance so small, because it's not actually 2 plates, it's 1 plate, and then the ions in solution. That was good. Okay, I know there were some other questions, but we will never get out of here if we do not move on to the last topic. And so who was the author was another group here? Can they stand up? Are they, yeah, good job. Are there things that they missed? Are there things you want to add? Okay. All right. Good job, guys. We are on to our very last presentation.
All right, last team, come on up.
Mehik, Andy, Sohan. And let's give them a round of applause.
Yeah.
Okay, so this is another example of the silver and yeast cells experiment. So here we have an anthropomorphic carrot in the very first slide, and then up there is an ant, and then what seems to be a housefly and a worm. And then on right here is a heart rate monitor, which stands at 85 beats per minute. In the next slide, we have the ant and the worm and the flies laying eggs inside the carrot, and the heart rate monitor is spiked up to 125. The third slide shows the very beginnings of the eggs hatching, and the heart rate has gone up to 260, and the carrots, like you can see the worms and the ants and all growing. The fourth and fifth slides are a continuation of that, with the heart rate being down at 35 as the carrot's slowly dying. And then finally we have all of the bugs fully developed, and the heart rate's at 0 because the carrot is now dead.
Okay, so I'm going to explain a little bit about this model. It basically conveys the mechanism in which the silver nanoparticles infiltrate and kind of sabotage the cellular membrane, indirectly causing apoptosis or just simply cell death. So if you look at the first panel right here of the personified carrot, what it is it basically symbolizes the yeast cell we use in our own lab. And there's a heart rate monitor, like Sohan said, attached to the body of the carrot. And what it does is it administers the health of the root vegetable, which is analogous to how we monitor the health of the yeast cell by evaluating its CO2 production, like I think other groups have mentioned before, by like the tube with the, like how far up the water went. And there are 3 different organisms trying to penetrate the skin of the carrot, and they clearly represent the 3 different types of silver we use in our lab. So we think that the ant represents the ions, so the silver ions, and the fly represents the silver powder, and the worm represents the nanoparticles. And as we move on to the next panel right here and down, we were shown that the insects enter the carrot through different means. And in the lab, we were shown that the silver doesn't directly harm the cells, but instead acts as a catalyst. And here the insects also don't directly deal damage to the carrots, but it's more of them like laying eggs. And it's also important to note that the insects deal different amounts of damage, with the nanoparticle worms doing the most damage. So you can see like the bones, quote unquote, of the carrot is being exposed here, obviously the most dangerous. And then the powder fly does a little tiny bit of damage. And finally, as the carrot's constitution is slowly weakened, the animals just leave and the vegetable dies, just like the yeast cells.
So this is a really nice and simple drawing. We were able to get the message like almost right away. There are some recommendations that we have. So we wanted to say like, since the fly represents the silver powder, usually the silver powder, the crystals of the silver powder is unable to enter the cell. So we would recommend that they make it so that the fly in the top right corner of the carrot isn't even able to like have access to the carrot, but more does like a little bit of damage from like the outside. And then we also would recommend that they emphasize the methods of entry that the different types of silver have. So like, for example, the nanoparticles, they disguise themselves as potassium ions, and they enter through through endocytosis. So we were saying like maybe they could show that a little bit more instead of just having the worms coming through the ground and stuff. There are a lot of things we liked about this drawing. We liked the simplistic and like cute art style. We appreciated the like how the silver are like laying eggs instead of like actually damaging the carrot, like how silver creates oxygen radicals instead of actually harming the cell. The reactive oxygen species are the ones that break up the membrane and do the damage. We also like the analogy. It worked very well for this topic, and yeah, overall we really like the drawing. Thank you.
Thank you for listening.
Okay, questions? We're waiting for that reception. I'm sure there's somebody here who's not going to get to go because they haven't asked any questions yet. You get to go, but we appreciate your question anyway.
Can you explain how the change in heart rate monitor relates to the experiment?
Yeah, so in the experiment, we had 5 different trials, each using the different type of silver that we could have used, so silver powder, silver ions, and then nanoparticles. So there we measured the different amount of CO2 produced. So the yeast would constantly keep producing CO2 until eventually died. And the more CO2 produced, the harder it was for the silver to kill off the yeast, and the more the yeast survived. So this is kind of in the same way in the, you can see the damage over time. It's not really, you can't really see how the different bugs like the worms, the ants, and the flies have their own effect on the heart rate, but it does show that how the carrot is dying over time through this process.
Okay, so my question is, similar to the last one, what concept is not captured in this cartoon that was sort of fundamental to the lab?
Well, I think the size difference, which is astronomical between like either the powder to the nanoparticle to the ion, is not clearly demonstrated in this analogy.
So what would be one way one could potentially fix that easily by changing some aspect of this?
Well, maybe if the like the worms were a lot smaller, or they were like just bacteria or virus that's infiltrating the carrot instead of maybe like a big worm. So,
although the ant to the worm size scale is not so bad. So what might be another way?
So we compared the flies to the silver powder that we use that doesn't enter the cell at all and has a low effect. So that fly could have been something else, like a larger bird maybe, or a much larger creature.
Yeah. I think if the fly was a great big creature, then the size scale would be much more captured. Because the nanoparticles are only maybe made of 10,000 atoms. So they're bigger than, I'm sure there's ants and worms that differ in size by about a volume fraction of 10,000. But the fly is not the astronomically larger things of the silver powders.
maybe we can have a bear or something. That.
Yeah. A big bird would be great.
Yeah.
Okay. Okay. Anybody else? One more question. Rita, you want to end with one more question?
Well, maybe this is thinking a little bit too much into it, but if you were to go with something like a bird or a bear, I feel like that would lose one aspect of this drawing that is really good, that I appreciate, especially compared to a lot of the other drawings that we tended to see. What do you think that is referring to?
Would that be like the way that the different types of silver are actually doing damage? Because like a bird wouldn't be able to lay eggs the same way an insect would.
Yeah, so the one nice thing about this is that they're all damaging the carrot the same way in the end, whereas a big creature may not be able to do that kind of damage to the carrot.
Yeah, because in the end, they're all delivering silver ions. It's just how well they can get into the cell to deliver those silver ions. And the silver ions themselves don't get in as well as the nanoparticles. Just one correction. The nanoparticles are about the same size as probably just like a lump of food. You said that you were describing endocytosis, and I don't remember what you said, but what they're mimicking is like a lump of carbohydrate or sugar or something that the cell would actually want to eat. Okay, so can the author please stand up? So is there anything we'd like to add? No, I think they did a good job. Okay, all right. Thank you.
Want to make any final remarks?
Okay, So we've decided that the parents asked enough questions. You all get to go to the reception. All right, so I just want to thank everybody. Thank you, parents, for lending us your children for a week. Thank you, campers, for doing a really awesome job with a whole pile of experiments. And I hope that you've had a great week, and we've had a great time working with you. So thank you.